So we are in the last section of this week's content. So now we will be looking at how to build Python models on time series data. Okay. So basically we will be building a couple of models that we saw in the theory. Okay. To get started with, we will be using data that is loaded in Google Drive. So we will just share the data that we are using in this exercise for you to play around with the data. And just like in how in machine learning or in the fraud detection we use scikit-learn, we will be using something called a stats model, um, and this has a lot of packages for working with time series based models. Okay. So let's first mount the Google Drive. So this step is really essential. We could have your data in Google Drive, and you could connect Google Drive to your Colab environment. Okay. Um, so I'm just going to import the plot ACF and plot PACF functions that are available in the stats models package, and let's try to work with that. So we are just trying to load a sample data. So we have just taken the sales data of a company, and I'll just plot it and show how it looks like. Okay, so this is how, I mean, this is a sample data that we are going to work with, and here in x-axis you can consider it as the time measured in some unit, and y-axis could be the sales. Okay, so you can see that the sales is initially decreasing and then is increasing. So this is definitely not a stationary time series. The mean is fluctuating. It's not constant. Initially it's coming down and then the trend is going up. So let's try to do some kind of transformation to this, and try to bring it to stationary form. Okay. So there is this quick function called diff, np.diff. So this will typically help us in computing the lag version of the variable. So if you remember in the previous or in some time back, we were basically trying to find out the difference by ourselves, right? If I just scroll up a little bit, you will be able to see that here we are basically detrending it, where we find out the lagged value of the variable by manually writing a for loop. But there is a quick option for us, whereby we can just call this np.diff function and pass in the data for which we want to find the lagged variable, and this takes an argument n, where this corresponds to how many th lag I have to compute. If n is going to be 7, it's going to compute the 7th lag variable. Okay, if n is going to be 12, it's going to be the 12th lag variable. So in this case we are just going to resort to 1. We're just going to experiment and see how this works, and I'm just storing the result in this variable called transformed. And once it is done, let's try to plot it and see. So we more or less transform the data to stationary. So there is no trend component. Visually speaking, there is not much of trend happening in this data. We have detrended the data, and we don't see much of stationary seasonality here. So we're all good with respect to seasonality. Okay, so now let's try to find out the PACF and ACF plots. Again, it's very easy to find out the PACF and ACF plots, and before one has to before one starts building a model, be it any model, be it AR, simple AR, MA, or ARIMA or SARIMA, we have to compute the ACF and PACF plots to find out the how many lags they have to consider. So here we are going to build a simple ACF plot with 10 lags, and this is what we get. So from the data we see that it's okay for us to include the first two lagged variables for the MA process. Okay, that's what the ACF plot tells us, because ACF plot the correlation at variable 1 and variable 2 is significant. It's basically they are above the error bands, and if you go beyond 2, it's basically falling within the error band, so we are safe to ignore them. Likewise, when you try to find out the PACF plot, we will be seeing something else, something different. So now here we see that the lagged version of the variable at the lag 1 variable is positively correlated, highly positively correlated, but the lag 2 variable is negatively correlated. So it doesn't mean that I should ignore the lag 2. It's also contributing, but it's contributing in a negative sense. Basically, if the value of the lag 2 variable is high, the value at current time step will be low. That's the kind of relation that we need to infer from this. So from the PACF plot, we see that it's good enough for us to consider the top 3 lag variables 1, 2 and 3. So that's how one has to interpret the ACF and PACF plots and come up with the values of P and Q in ARIMA model. Now let's try to build a model itself. Okay, we haven't built any model as of now. We are just trying to analyze the data, dissect the data, do different kinds of charts on it, and see how the data is. So now let's try to actually build a model. So for this, I'm just going to use something called as the data coming from websites. So typically, this could represent the number of users who use or who log into the website or use the website on a daily basis. Okay, again this is just dummy data. Again this indicates a clear time series pattern. Okay, and that's a clear trend to it. As time increases, we see the incoming volume is trending up. Okay, so now again we are just going to resort to the same idea of dividing the data into train and test. Of course, one has to divide the data into train, val and test for performing all the hyperparameter tuning, but since all those are already covered in previous lectures, we are not going to do any hyperparameter tuning here. We are just going to build a simple model with one set of hyperparameters. So we are just going to divide the data into train and test alone. So what I am going to do here is I am just going to create a Boolean array called MSK mask, where I am just going to take the last 30 days as test and the remaining data as train. Okay, so this is really essential when you do the train test split in a time series data. So previously when we saw the fraud detection problems, or in the past when you did any machine learning problem, you would have divided the data into train and test using random split or some kind of stratification. Okay, but again it's still random, and that's perfectly fine because there is no time component involved in that. But this is a model where there is time component involved, so you just cannot divide the data randomly as train and test. There should be some time component involved associated in dividing the data into train and test. Okay, so typically what is going to happen is maybe let's say we are trying to collect 2 years of stock data for predicting the future. So in this case, maybe we could use the first 20 months for training, and the next 2 months for validation, and the last 2 months for testing. So there should be some kind of time taken into consideration when we divide the data into train and test. It should not be random split, and one has to keep this in mind when they build a time series based model. And this applies for any time series based model, not only for ARIMA, it applies even for any deep learning based time series models. So that's what I'm doing here. I'm just going to create a mask array where the first 3 values will be last 30 values will be false, and the remaining values will be true, and I'm just going to use this masked array for dividing my data into train and test. Okay, so sometime back when we were discussing about the stationarity of time series, we were doing some visual inspections to see if the time series is stationary or not, right? But that is not the case, but that won't work always because this visual inspection is not a foolproof mechanism. What looks normal, or what looks like detrended data for someone might look like a data with a slight trend, and what looks like data with no seasonality could look like a data with seasonality to someone else. So we need to have some statistical tests, just like how we have the test of means and ANOVA, things like that. We have this test called uh, Dickey-Fuller test or augmented Dickey-Fuller test. That's what we are going to do now. Okay, again it's there in stats models, and the name of the function is ADF Fuller. Okay, and here the null hypothesis of the AD Fuller test is basically the series is non-stationary. That's going to be the null hypothesis, and your alternate hypothesis is that the time series is stationary. So again we just follow the same rubric of the hypothesis testing. We have a null and alternate hypothesis. We define critical value and we find the p value. If p is less than alpha, which is the threshold for which is the critical value, we say we reject the null hypothesis, and if p is greater than alpha, we fail to reject the null hypothesis. Basically we do not have enough evidence to prove against the null hypothesis. So when we just have to pass in the data directly to this AD Fuller function, and let's see what the result is. Okay, so the result is going to be basically a composite like data. Okay, it is going to give you a couple of values, but uh, the second value whatever you are seeing here will be the p value. There are other additional values, just like how in a t test you get a t statistics, right? Like that you will be getting a test statistic here, which is the ADF test statistic, and then the p value. So for us the value of interest will be the p value, which is the second one. So here we see that the p value is going to be really high, and that's very true, right? The data whatever we have here is not stationary at all, and p value is really high. Generally the cutoff is 0.05 and here it's 0.74. So p is much greater than alpha, so we fail to reject the null hypothesis that the data is not stationary. So now let's try to do the transformation trick and make the data to stationary and then run the Dickey-Fuller test again. Okay, again I'm using this function called dot diff. I mean I'm just trying to give you different flavors of functions which one could use for accomplishing the same task. One could simply go by finding the difference in a simple for loop, or one could use the np.diff, or this this is a pandas the data frame, and you can also call the diff method of the data frame. Okay, and let me do the diff operation and plot it. So now more or less I would say that the data is stationary. Okay, of course there is some kind of seasonal pattern going on, but that is not very obvious. Okay, so these are the cases where it could trigger an argument, right? If you just go by visual inspection, some people say that there is no seasonality in the data, but someone else might say that there is seasonality in the data. So we resort to statistical test for doing that. Okay, now I pass the df train diff, which is nothing but the transform data, to this AD Fuller function, and now if you see the p value is going to be very less, 0.05, I mean 0.054. Let's assume that the let's be a bit like liberal and say the alpha is going to be the threshold is going to be 0.1, and the p value is going to be lesser than alpha, and we reject the null hypothesis that the data is non-stationary. Okay, so we reject the hypothesis that the data is non-stationary. So now let's try to plot the ACF and PACF plot, and so this is how it looks like. So we see that in the ACF plot the correlation is quite evident. We see correlation up to I would say maybe 7 till 7 lakhs the variable is correlated, it has some correlation. And likewise for PACF plot, maybe we could just resort to 2, and beyond 2 everything is going to be insignificant. Okay, and now we are going to build the ARIMA model, ARMA. Okay, so Again, we are just going to import it from the stats module. um, uh, so we are just going to pass in the train data, and then followed by that the order, the PDQ. Okay. So just keep this in mind. We are just going to pass in the raw data. We are just taking the raw data and we are just going to pass it as it is. We are not going to pass in the transform data, because this transformation will be automatically taken care in the ARIMA model. Okay. The PDQ. Okay. So I am just going to assume the P is going to be 2 in this case from the PACF, and Q is going to be 1. Just for the sake of simplicity, I am just going to build a model with just one error term. Okay. And the differencing is 1. This should be enough for us, because we saw that just by differencing 1 we were able to make the data stationary. Okay. And again I am going to fit the model using this method called dot fit, and that returns object from which we can see some of the summary statistics. So there are a lot of numbers over here. I'm not going to cover everything. We're just going to touch upon some of the important ones. So as this is a ARIMA process with p equal to 2, which means that there are two lagged variables. So there will be two coefficients. There will be one coefficient for the immediate lag variable, and there will be one more coefficient for the lag at time step t minus 2. So that is what I have here. I have this autoregressive part at L1 and autoregressive part at L2. There will be two coefficients, and I have the coefficient value here. Likewise, I have this MA part which corresponds to the value of the coefficient corresponding to the error, and I have this coefficient here, and also the mean, or whatever we call it, the sigma in this case. And we also have the corresponding p values. So this interpretation of p value is very similar to the p value that we interpret in the linear regression. So if the so this is built under the hypothesis that the coefficient is equal to 0. Null hypothesis is that coefficient is equal to 0, and alternate is that the coefficient is not equal to 0. So p less than alpha indicates the fact that we reject the null hypothesis that coefficient is equal to 0, and very high p value indicates that the coefficient is not significant for us. Okay. So yeah, so that's a quick way to interpret the results, and let's try to plot the residuals. Okay, let's try to plot the residuals and see. So residuals here, I mean the residuals that I get in the training data. I'm just going to use matplotlib for doing the same. Okay, I'm just going to take this model underscore fit, and I'm just going to get the residuals, and I'm just going to do a simple density plot. Basically, this is a PDF plot of the PDF, and this is a simple plotting of the residuals that I'm getting at every time step. So we see that the error is kind of normally distributed with mean 0. This is the PDF plot of the errors, and there is normal distribution of error. This is more or less fine, right? In case if I see some kind of pattern here, if the error is not normally distributed with mean 0, then there is something going on in the data which I am failing to capture. So in that case, my model is not accurate, I should say. So as one last check, let's try to find out the ACF and PACF plots of the residuals. So ideally, what should happen? The ACF and PACF plots should not have any correlation with the past. So basically, only for the lag at 0, which is the correlation with itself, it should be 1, and for remaining every lag, it should be 0. We'll just see if that is happening. Yeah, the data that the data that we have, the model that we have built produces residuals that are not autocorrelated. Had there been autocorrelation in the errors, then definitely we would have seen some spikes apart from 0. We see some spike here, but that's because this model is a very generic, a simple model that we built. But typically speaking, there should not be any spike after the first spike, which is nothing but the correlation at lag 0. And now let's do one thing. Let's try to forecast the data, or let's try to forecast for the future. Okay, we have taken the last 30 time steps as test, right? And now let's try to predict with this model for the next 30 time steps, and see how the results are. Okay. So when we try to call the fit or forecast method, the way in which we call is slightly different. So in scikit-learn, we just call the predict method and pass in the test data to that. But here there's nothing like a test data, right? I just want to basically there's no feature. So basically here what I'm going to do is I'm just going to predict what is the value of it going to be in the next 30 time steps. Okay, at time step t, I'm just going to predict how my predictions will look like 30 time steps in the future. That is what I'm doing here. I'm just going to call the forecast method and pass in the length of the test data, which is nothing but 30 in this case. And I'm just going to create a column called forecast manual, and for the first or for the first 270 odd data points or rows, I'll have like set it as none because they are the part of the training set, and for the last 30 I'll have it from the forecast test variable. And now if I try to plot, let's see what happens. Yeah, we are getting some predictions, but of course the prediction is not that great. So modeling a time series data is not so straightforward. It is quite easy to build a model for predicting non-time series based data, but when we start working with time series, things tend to get slightly complicated and tricky. Okay, so it involves better, or it needs better tuning of hyperparameters and defining the orders p, q and d properly. But yeah, so here itself we see that the actual values after this point are going down, but our predictions are upper, I mean higher. Again, this indicates that the model is not as good as it should be. So that concludes the end of this week's content. So just to summarize this week's content, we started off by defining what time series is, why time series is so special, why it needs a separate treatment, and after that we saw some of the components of a time series, which are trend, seasonality and cyclicity. And also we saw what stationarity in time series mean, and some of the tricks that one could resort to for transforming a non time series data to a time series data. And after that we saw how one could start building models. So we saw the simple autoregressive model, which is basically making use of the previous values of the same like variable. It could be lag 1 or lag 2, and then we saw how to determine the order using the ACF and PACF plots, and then we saw about the moving average model, which predominantly makes use of the errors in the previous time steps that we have made. And then we saw about the ARIMA model, which is nothing but the integration of AR and MA models. And then we saw the ARIMA model, whereby we take a like data which is not stationary in nature, which has some kind of trend component, and we try to detrend it using the differencing trick, and we use the same idea as ARIMA. And then we saw like SARIMA, which is an extension over ARIMA, where the data has both trend and seasonality, and it has 4 parameters p, d, q and m, where 2 parameters are for detrending and deseasonalizing the data, and there are 2 parameters p and q, which is for the moving average, sorry, autoregressive and moving average paths. And we also saw a hands-on exercise on how to build a time series model, and we did a couple of exploration with the data by plotting PACF, ACF plots, on how one to read these plots. So that summarizes this week's content. So as I said before, time series is very essential in the world of finance. Any financial sector you see will definitely be working on some kind of stock price prediction, or even in the non-financial world like sales forecasting. So any process where time component is involved, we need to use, or we need to start thinking these problems using time series models. So with that, I conclude this week's lecture. Thank you.